Okay. Okay, so let's have a class. This will be our last lecture, then we move on to the presentation. So we will talk about is antimicrobials. That is usually teach in a for the microbiology class. But in the for the chemistry class, we will mention some microbiology, but more important, we will focus is on chemistry standpoints. Okay, so antimicrobials, number one, what we are talking about here, we want to talk about is organic acids. Okay, that's what we're gonna focus. So organic acids, this is usually we say it is natural existing in foods. And we could be chemical synthesized. And the majority of these is short chain fatty acids. And we will give you 5 examples, and we go from there, talk about each of the chemistry. And these, we all say it's GRAS status. So what this means, every antimicrobials used in the food products, first of all, they have to be approved by EPA. That is Environmental Protection Agency, which is environmental friendly. Then you have to approve it by 2 agencies, which is FDA and USDA, FSIS. So Food and Drug Administration and the United States Department of Agriculture, Food Safety and Inspection Service. Now for FDA, there is responsible for the food products is basically like a produce, like juice and others. And FSIS usually is meat, egg, and poultry products. Now this egg is usually we call it a processed egg. Okay, if it's raw egg, it's in FDA. Now, what means GRAS, which means generally recognized as safe, which means they are generally recognized as safe using in the food products. Now how they use it, there is basically 3 methods. Is number 1, you can do a spray on the surface. Number 2, you can do a dip in the solutions. Number 3, you can do as ingredients. And regarding the list of the GRAS, if you look at the FSIS website, there is a long list. About maybe 50 to 100 of those chemicals approved to be used on the meat, poultry, and egg products. And the FDA in 1996 has also a list about like 10 approved to be using on the food contact surfaces. And the EPA, of course, has to be approved before that, which is environmental friendly. So this is most of these organic acids, all of them are GRAS, generally recognized as safe. Okay, so these are the things we want to mention. Now, from the chemistry standpoint, we want to mention one thing is that all these organic acids has to be used close to or below the pKa value. And should not be used or will lose effect when they more than pH 5.5 food products. So this is its limitation. Very unfortunately, there's some limitation about that. Okay, we will get to these things later on. What is pKa? What is the mechanism behind that? Now, the next thing what we're going to here talk about is give you some examples. What are these short-chain fatty acids, so-called antimicrobial organic acids? What are they? So we're going to give you some of the examples. Okay, so the examples will be right here. Okay, number one, acetic acid. Okay, what is the acetic acid chemical looks like? Chemical formula: CH3COOH. So well, let's write that. Name, formula, FOR, formula, right here. And the pKa value, and the food products, and the microorganism, and the last one will be the concentration. Okay, what's the pKa value for acetic acids? So pKa value for acetic acids is 4.5. Now, where they come from? The food products. We know vinegar. Okay, what's the microorganism impacts? Bacteria, but more impact is yeast. What is the concentration? 0.1 to 0.8%. This is the first one, acetic acid. Okay, how about the second one? Second one, benzoic acid. And we will talk more later on. Benzoic acid is a benzene and COOH, carboxy group. What's the pKa value? Very low, 4.2. Where they comes from? Cranberry. Now, what's the impact for the microorganism? Bacteria. Okay, some yeast. What's the concentration? Less than 0.1 to 0.3%. Okay, the next one. Lactic acid. What's the formula of lactic acid? CH3, COH, H, and COOH. What's the pKa value? 4.8. Where it comes from? Fermented products. Okay, fermented foods. What's the impact for a microorganism? Bacteria, yeast. What is the concentration? 0.4 to 2.0%. Okay, that's lactic acid. What's the next one? Probionic acids. Okay, what's that? CH3, CH2, COOH. That's pKa value 4.9. Where this comes from? Swiss cheese. And we talk about it. Major impact is for yeast. Little bit for bacteria. This concentration around 0.3%. Okay, last one. Sorbic acids. Okay, what is sorbic acid? The formula looks like CH3, CH, double bond CH, CH, double bond CH, and COOH. Where it comes from? Green berry. Okay, impact for bacteria, for yeast. The concentration, this is probably somewhere around 0.1 to 0.3%.
What's the pK?
The pK value here is 4.7. It's a good question, 4.7. Okay, now you notice that this pKa value is very low. Can you see it? So first question, what is pKa value? pKa value, remember, I could write RCOOH. Is that right? This is protonated gases. All these acidic acid, benzoic acid, lactic acid, propionic acid, sorbic acids, these we call it a weak acid. What's the difference between the weak acid and strong acid we call it? Difference between hypochloric acid, hyposulfuric acids. Okay, those are strong acids. They could be dissociated, become what? OCOO and proton. Is that right? They could become like that. So what's the pK value? The pK value is the pH value at which the concentration of associated formation formed equals dissociated. You can say it's dissociated equals undissociated. That is a pK value. So this pK value is very low. So there is a restriction. Now, what is that restriction comes from? Why there is that restriction come from? And said very simple, is undissociated form allow into a bacterial cell or a microorganism cell. Okay, so I'm going to give you an example. We're going to talk about the mechanism behind this. What is the mechanism? We're basically going to talk about the antimicrobial mechanism. What is that? Okay. First of all, we talk about the pH neutral is at 7. But in a real life, we have two situations. pH around 4 and the pH will be more than 7. Let's say pH around 9, for example. This is a neutral status. This is acid. This is alkaline environments. What is it going to be looks like? If it's in an acid environment, okay, then the ROO, the dissociated form will be reacted with the proton, then become the unassociated form, RCOH. In a pH 9, you go to the opposite direction, which means ROOH will become dissociated ions and the proton. Okay, I have a bacterial cell. A bacterial cell is this, very large. Okay, let's say I have a bacterial cell. What's the pH of a bacterial cell? Basically, the pH is around 6 to 7. We can even say 6.7, 6.8, close to neutral. And I said that antimicrobials go into a bacterial cell. Only this undissociated form will be allowed to come in, and dissociated form will not penetrate, or very limited. So only this guy gonna come in. Okay, when this guy comes, what's gonna happen? This ROOH, because it's pH 7, will dissociate, become dissociated from it, and very important is a proton. And this proton is acid. Now, once you have an acid there, what's the problem? The bacteria don't like it, is that right? Because it's going to kill in the bacteria, cause imbalance. So they have to repel outside of the cell membrane. They have to repel out of cell membrane. Okay, what they needed is energy. Is that right? They need ATP. Now where going to be the ATP comes? ADP with PI, then with what? Is enzyme called ATPase. So what this means for the bacteria? I'm going to repel all these protons outside of the cell membrane, so I have to synthesize ATP and also hydrolyze it, called B. What's going to happen? I'm going to be spending extra currency money, which means it's going to be exhausted, is that right? That's called metabolic imbalance. So, metabolic disorder. So what happened? The bacteria could be inhibited. And some bacteria may be died. So that's a reason this pH value, this pK value is important. Why? Because only on the associated format will be allow them to come in. If you are using a little bit higher, this concentration will be low. And the researcher has been showing us, remember pH is equals minus log 10, the proton concentration. So about 1 unit of pH increase, it will be at least 90% of the effective organic gases, undissociated form, will missing. This is approximately people evaluate. So let's say this is pH 4. If it we increase to pH 5, the amount of that will be significantly decreased. Somewhere will be 90%, somewhere will be 50%, close to 90%. Therefore, the amount of effective concentration going here, bacterial cell, will be significantly decreased. So they lose their optimal antimicrobial efficacy. Now there is something I also want to mention. Majority of these organic acids, their antimicrobials, we call impact, we call it inhibition. Okay. If you take in my general microbiology class, we have a terminology for that. It's called static. Is that right? It is not really killing bacteria. If it's killing bacteria, we have another terminology. We call it side-up. Now why? We use energy currencies, ATP. The bacteria sometimes have GTP, CTP, UTP, all those things could be as a backup energy resource. And they also have a different bypassway to generate more energy to balance it. So this is only temporary to inhibit the bacterial growth. Now what means inhibit? This is a normal bacterial growth curve. Is that right? We had a number, y-axis. This is time. Then we have a lag phase, log phase, stationary phase, and death phase. What means inhibit? This lag phase will be long and then grow a little bit, something like this. And this curve, we will call it inhibition. So, what this means, the bacteria is still there. If there is a 1 log, 10 cells in the food products, it's still there. We will delay the growth to 2 log to 3 log. That's what's a function of these antimicrobials, of these organic acids. And that's why you find some products in the market, they all have a shelf life. You can't put there for a couple of years because at the end of the day, it will grow. Because it's only inhibited the bacterial growth, which means delay the growth. You can understand it. They are not killing bacteria. If they're killing bacteria, this curve is like this. Okay? So that's something I want to mention. Now, they don't have a problem. You look at here. This pK value is very low for acidic acids. Is that right? Acidic acids. CH3, COOH. This pK value is only 4.5. What's the pH of a meat product? And we talk about that. Around 5.5. Okay, what we should do? It seems like if I use it, it's going to lose the function. What we do? We add with a salt. Okay, that's one of the methods we do. We will react it with CH3, COO. This is we call it sodium acetal. And then becomes what? CH3, CO, CH3, go here, C, and then we combine this. What is this? Sodium diacetate. This could increase the pK value to 5.4. This is a major, and about the concentration 0.25, is a major antimicrobials in our ready-to-eat meat. If you buy a hot dog, you buy a frankfurters, a vacuum package, or a ham, when you look at the label, it will say sodium diacetate there. It is antimicrobials. It is come from here. There is two things good for sodium diacetate. Why? The pK value, number one, is improved from 4.5 for acetic acids to 5.4. The second thing, this is a salt. So the salt formation is easily dissolved in water. And that means it's easily to do the preparation. Okay, so this is one of the methods we solve the problem. We are making them as a salt, some of them. Okay, now the question here. Benzoic acids. Okay, this is the example number one. Make sure this is covered here. Okay, now we move on to talk about benzoic acids. Benzoic gases, what it looks like. We draw it already. What is the pK value? Very low. 4.2. That obviously means lots of products we cannot using. It's lose impact. Unless it's like acid, a very acid juice or something. Then what we do? And the people are really smart, the scientists. This is the carboxygens, is that right? We're doing the methods is a esterification of carboxyl acid. So what it looks like? It become a long chain carbo with benzoic and the acid connection. And I gave you several examples. Example number 1. Good. Benzoic acids. OH. I'm going to react it with this guy. What is this? Meso. What gonna be looks like? Is this gonna go become a water? So what it looks like? Okay, what is this called? Meso benzoic O8. What is O8E means? Ester. Okay, this is the first example. Okay, second example. Same thing, you can do by yourself. I had benzoic acids. Little bit complicated. I'm gonna work with ethanol. So what it looks like? Therefore, what is called? Ethyl benzoic O8. Okay? Now again, right here. Become a water. Okay, I'll give you number 3 example. I have this benzoic acids, carboxygens. I'm going to be a little bit longer. What is this guy? Propanol, is that right? Propanol. They become what? CH2, CH3. This is propyl benzoic O8. This could be also this loose of water right here, hydrolyzed. This could be go on and on and on. The next one will be bitanol, and we can go several, okay? And you could have something reacted. This will become the final one, using a food products, people really like it, is this guy. Benzoic OH. You can do on and on and on. Why people wants to do that? Once you have esterified, this pK value will increase into 8.5. What this means? Which means any food products, your pH range in 3 to 8. It's a widely broad pH value, which means from acid to a weak alkaline, they all could be used. Can you see it? So this is a wide range of foods. Now, are these really all accepted? Not really. People need to do a validation study for their.
Where's the acidic hydrogen on that? Like, are they still acids?
Where?
Like 1, 2, and 3, and like so on. Like, where is the hydrogen coming from? Like, where's the acid, like the acidic hydrogen?
Acidic hydrogen, what that mean? What that means?
Like, they're acids, right?
Yeah,
Which hydrogen comes off?
this comes out right here. Where you think it is missing?
Like, for benzoic acid, the OH group, the H is the acidic hydrogen, so that's like the proton that is the acid.
Yeah, that is the acid, yeah.
So which hydrogen on those, like methyl benzoic OH, like which hydrogen on there is the acidic hydrogen?
There is nothing here. It's all become ester formed.
Okay.
Yeah, it's all missing. It's hydrolyzed.
So how does it have a pKa?
They will be hydrolyzed. Yeah. They still have a pK value here. These whole products have a pK value. Yeah. Let me double check it. I think so.
Is that why they say to drink cranberry for urinary tract infections because
Yeah.
of the bacteria?
Yeah, it all become benzoate. It's true, it's all become benzoate. They have a pK value
Okay.
because the pK value is
It doesn't have to be
is
acid to
increased.
have a pK value.
It is increased.
It's less acidic because it's not an acid.
Yeah.
Oh. Okay.
Yeah. Did you get it?
Yeah.
Because it's less acid. That's why it is increased.
Okay.
Yeah, he thought
And
that
this
it
is
was
still will be a little bit to go there. We should draw like this. And then become this guy. Their pK value is increased.
Okay.
It's not the acid format anymore. And I should draw this there.
Okay.
You know what I'm saying? What we're talking about here is this pK value. Then, when we talk about here, it's go here. Okay, this pK value should go that way. Okay, then that's increased a lot. Okay, that's a good question. That's a good question. Yeah, let's go the other side. Okay, so because it's increased the pK value, so that's a range it's increased. Okay, now, so now the thing is that are these all approved to be used? Some of them. The methyl benzoate is approved to be used. Propanol benzoate is approved to be used, and hepo is approved to be used. Ethyl benzoate and another one which is bitorial benzoate is only conditionally approved in some of the countries. It's not in the United States. It's approved used to the only food products.
There's sodium benzoate too.
Yes, then you have to add a sodium somewhere.
Okay, I was gonna say, I see that in a lot of food.
Yeah,
Sodium is-
then you have to add a sodium somewhere. Okay, now, once this is done, people find it. What's another thing they find it? This chain length is longer. Once this chain length is increased, what happened? The antimicrobial efficacy is also increased. However, they are difficult to dissolve in water. So, what's the limitation for that? These ester, you're right, if you want to use it in your food products, you have to become a salt. Or they can only using in like a composed products as ingredients. And the kind of those products is sometimes a little bit high fat, lipids there, because they can have kind of like an emulsification impacts there, that they can mix them. Because they are not easily to be dissolved in the water. And they also could be using in beer products. Okay, or some fermented products. Do have some limitation about that.
Higher oil binding.
Yes, yes, they're not gonna just go ahead to use it because they're very difficult to use in the water. They're the organic chemicals. Okay, so from here we're gonna talk about these basic organic acids, the idea what it is. So I'm gonna turn this off. Then